Welcome back to Industrial Problem Solving. My name is Dave Roysum. In this and in the next several modules, we will cover the core of problem solving. That is, figuring out how the problem works. Before we begin, let's take a look at where we are going in the central part of the course. In this module, we will talk a bit about science and then a bit about statistics. Obviously, we can't teach science or statistics in 15 semesters, much less 15 minutes. What we can do, however, is to mention where each is best suited and some places where they may not be well suited. In the next module, we will cover some of the most famous of the formal problem-solving methods. Again, we will have a few words to say about where they may work well and where they may not work as well. In the modules following that, we will explore in more detail my favorite methods, and that is the street smart methods. While science is the oldest and most practiced of the problem-solving methods, in some ways it is also the most misunderstood. Even scientists don't always know how it is best applied, particularly in the field. Science teaches us three things for a very well-defined problem that may have already been studied. For this well-defined problem, science teaches us which knobs to turn, what direction to turn those knobs, and how far to turn those knobs. It is the how far that is the expensive part of science. That requires the schooling, the instruments to gather the numbers, and the analysis. That leads many to think that you need to pull out the calculator or spreadsheet to practice science. That seems to leave many people out. Yet, wouldn't it be helpful just to know which knobs to turn and which direction to turn them? It certainly would. It would help us avoid wasting our time and our money on knobs that are not as likely to be strongly connected to our problem and thus not as likely to be helpful. It might help us avoid the frustration and embarrassment of turning knobs that won't make our lives noticeably better. As we see, we don't necessarily need numbers to apply or use science. So, what about the how far? The predictive part of science. How do we figure that out in the field? Simple. Turn one of those connected knobs, and if it doesn't help enough, turn it farther. If you peg that knob and still don't get far enough, rebuild that knob or find another one. Only when you've exhausted all of the known knobs do you have any business looking for others. Yet, as powerful and useful as science is, it still has many, many limitations. As we've already mentioned, it can be terribly and awfully expensive. Often you will not know how well a model works until you've tried it, and then, perhaps not even then. Maybe the improvement you thought you made was just random fluctuation. Or perhaps the model missed opportunities. Perhaps, worst of all, many of the problems that we work on are not modeled at all, and perhaps not even studied. Despite these limitations, science can be very helpful on problems already studied. Science also has the gift of prophecy. By that, I mean that you can make educated guesses about things not yet studied. Let me give you an example that we cover in my Web 101 class. That is the question of whether a bowed roller can spread a baggy edge. The answer is not likely. But let's see how we got there. From Web 101, we know that 1. A baggy edge has no tension, and that 2. If we have no tension, we cannot have any traction. And 3. If we have no traction, we have no bowed roller spreading. Still, we always have to be humble. Maybe there is some as yet unidentified spreading mechanism that would allow us to spread that baggy web. The prudent practitioner would simply try things, but make no promises, and see what the system actually does rather than what we expect it to do. Many technical people have already had formal training in statistics. Perhaps this was just a single course in college, or maybe later in a Six Sigma program. Like science, statistics is very expensive to acquire and even more expensive to use. Like science, statistics can also be abused. Perhaps the most common is to data mine to search for connections. Even if there were a connection, even a statistical one, that does not mean the connection is causal. For cause, we must turn to science. Thus, statistics is best used to suggest theories when none exist at this moment. And that is the role of research. Or, another application is to verify theories that have already been established by science, in which case statistics is a subservient and secondary tool. An example of data abuse is to Six Sigma a problem such as wound roll corrugations. Science and plenty of experience already tells us what causes corrugations. We should not hope that another tool will give us answers that we like better than to level your profile and wind looser. The same applies with wrinkling and tension control issues and many other problems that we might see in our web equipment. Perhaps the most puzzling aspect of statistics is that of sample size. Simply stated, it is how many readings you need to have in order to be reasonably sure of a connection between two variables. This answer can be all over the map. In one extreme, it may take 10,000 rolls at a printing press to tell which of two suppliers makes paper that breaks less when the break rates are in the normal range of a few percent. There are several reasons for needing these 10,000 rolls. The web break is uncommon in any particular roll, which always ups the required sample size. The second is that materials are not the only variable. There are two strong confounding factors that can seldom be controlled for. One is the printing press machine and its operation. The other is the environmental humidity, which is probably the strongest factor of all and is seasonally uncontrolled in most plants. On the other extreme, also continuing with the web break theme, is a web break during acceleration. A single web break is usually enough evidence that tension controls is probably poor during that challenging event. A conclusion based on lots of previous science and experience. The statistics are that the likelihood of a break during a 1-minute acceleration event is unlikely to be mere chance, when a typical production run may be hours long. If brakes favor the momentary acceleration instead of the hours-long run, that momentary acceleration is troubled, and few examples are needed to justify that thinking. Another concept that needs consideration is the trade-off between sample size and risk. If we use small moves, we are not so likely to wreck production. However, we then need really large sample sizes and the discipline to hold settings for hours or days and hope that nothing else drifts too much. On the other hand, if we make really big moves, we are likely to make defects. However, if we use good judgment, we might get the answers we are looking for in a couple of minutes or just a few rolls. Since I personally do not have much time as a consultant, usually just a few hours, I use this big move, big risk strategy. To know how far or how big of a move to make, I will often ask the operator, "How far do you think we can move the knob without breaking down?" I make it clear that it is okay to make defects, just not so much trouble as to shut the machine down. Very early on, I developed a distrust of instruments. While some were okay, and perhaps some were even good, others were little better than random number generators. So in 1988, I wrote a paper on roll quality measurement. That was the most widely reprinted article that I ever penned. In it, I showed how to first determine if an instrument can resolve a difference that was small but important. And second, how many measurements or readings each instrument or technique needed. The method I developed was simple. First, put a violent and known upset and winding into a wound roll. Second, measure on each side of that change. Third, use statistics to determine confidence in the ability to see a large change and extrapolate how many measurements were needed to see a smaller and thus more practical upset. As I suspected, the results varied from good to worse than worthless, and that there were some application or grade sensitivities. Nothing but some first-year statistics to test the tester, so to speak. I want to close with one very important idea. That is, that some types of data have more worth than others, everything else being equal. Analog data is worth much, much more than binary yes-no data that QA often uses to reject products visually. An example is the number of defects in a roll versus whether a roll contains a defect or not. If one roll had 10 defects and another just one defect in it, QA would rank them the same, defective. However, the troubleshooter would notice a reduction of defects and make use of that information. Worse yet, or perhaps even worse than worthless, is opinion, or anecdote, or hearsay. Thank you so very much for joining me in this continuation to the problem-solving process. In the next clip, we will continue our tour of formal methods. Stay tuned.